Hi. We have been discussing magnetic fields, and today I would like to start from reminding you some important facts about magnetic field which we discussed last time. The first fact was established by Ørsted in 1820, and it was related to a straight current, a straight wire with current, constant current, and it was established with the help of a small magnetized needles that the straight current creates a magnetic field, and the magnetic field lines are arranged as concentric circles with the center in the straight wire with the current. And these concentric circles lie in a plane which is perpendicular to the straight current. And the magnetic field in any point of observation, which is described by a vector of magnetic induction, is given by the magnitude of this vector is given by the following formula, which is mu 0 mu h, where mu 0 is the magnetic constant, which is 4 pi 10 to the minus 7 in the international system of measurements, system of units. And mu is the magnetic permeability of the medium which fills this space, and h is the magnetic field strength, which is which equals, in this particular case, it's proportional to the strength of the current and inversely proportional to 2 pi r, where r is the distance from the point of observation to the straight current. The existence of such field was discovered by Hans Christian Ørsted in 1820 in the 19th century. The second fact which we discussed consisted in the action of magnetic field, the creation of magnetic field in a wire which is bent in such a way that it forms a spiral or a coil. So if we take this wire and arrange a coil and let the current I flow through this coil, which is also called a solenoid, especially when it has a metal core, iron core inside it, then the magnetic field inside the core, inside the solenoid, turns out to be uniform, and the inductance of magnetic field is defined by this formula. Again, mu 0 and mu and h, where h is proportional to the current strength flowing here and directly proportional to the number of wire turns per unit length. So it may be put also as the unit length, the length, the total length, say L, divided by the total number of turns of this wire, which forms a coil. So if you have a straight electrical current, it creates a circular magnetic field around it. If you have a circular magnetic current which flows along such a coil, then it creates magnetic field which is uniform inside this solenoid, and which is which looks like the magnetic field of the bar magnet. If we observe the magnetic field in the outside space, it will look like this, and inside it will be a uniform magnetic field. Then we also considered the action of magnetic field, uniform magnetic field, on a current. So if we have a straight current and a magnetic field perpendicular to the straight current, for example, magnetic field looking from the blackboard to this hole, such magnetic field is denoted by such symbols. That is the magnetic field induction, which looks in this direction, and we have a straight current in this uniform magnetic field. Then there will be a force acting on the current, on the wire with the current, a force from the magnetic field, and this force can be the direction of this force can be determined using the left hand rule, when you put your forefingers in the direction of the current and your palm in such a way that the magnetic field vector enters your palm. Then your thumb will show the direction of the force acting on this straight current, and the force will be proportional to the current and proportional to the length L of the wire on which the force is acting. The longer the wire, the larger the force, and also proportional to magnetic field induction. The larger the field, the larger the magnetic field, the larger will be the force acting on the current. And then we discussed also the action of magnetic field on a current loop. So if we take a current loop, let it be of rectangular form. So the current flows here, and then it flows here and here. If we have such a current loop, that is a wire bent in such a way, and suppose we have a magnetic field here, and this time let the magnetic field be directed towards the blackboard. That is the vector of magnetic field going from the audience to the blackboard. Such a situation is denoted by such symbol. That is the magnetic field vector going to the blackboard. It looks like an arrow which is directed in this way. So if we have such magnetic field here, then the magnetic field will exert some force, some action, will act on this current. Due to this law, the force will be exerted on this portion of the current. So if we take this dimension like delta x, and this dimension will be delta y, for example. So the area of this rectangular loop will be delta x times delta y, and in this case the external magnetic field will be acting with some force on this portion of the wire, and this force will be, according to the previous formula, will be defined by the strength of the current, electric current, and the magnetic induction, and the length of this wire with the current. And the same force will act on the opposite section of the current. So in this case, the force will be directed if the magnetic field goes in your palm and the four fingers show the direction of the current, then the force will be directed along this. Will have this direction, and another force will have this direction. So the force acting on the loop with the current will act both on this section of the current and on this section of the current. And these two forces will compensate each other because they will be directed oppositely. If the magnetic field changes its direction and magnetic field induction vector is directed here from the blackboard to the audience, then these forces will change their direction, and they will be directed outward, trying to expand the magnetic loop. In this case, no torque, no mechanical torque acts on the loop with the current. But suppose the magnetic field is directed in the plane of this loop. Suppose the magnetic field is has this direction. The magnetic field induction vector lies in the plane of this loop. Then the figure will show you that one force will act on this part of the current. The force will be directed towards the audience, and the force acting on the opposite part of the current will be directed in the opposite side into the blackboard. So these two forces in this particular case will form a torque acting on the loop, and this torque will tend to rotate the loop, and the torque will be defined according to definition of torque. It will be equal to the force times the arm of the force, and we may take any axis of rotation here in order to calculate the arm of the torque. We may take this axis of rotation which goes through the center of this loop. Then we will have to multiply force by delta y over 2, and then add another torque from another force directed, tending to direct the loop in the same direction, and it will also be equal to F times delta y over 2. Or we may assume that the axis of rotation is here, and then the torque of this force, of the first force, will not have any arm. The arm will be 0, and we will have to take into account only the torque of the second force, and it will be equal F delta y. Anyway, no matter what axis of rotation you take for consideration, the final result will be the same. The torque acting on the current loop from the magnetic field will be defined as F delta y, where delta y is the, in this case, horizontal dimension of the current loop. And if we know the force, we can substitute this expression for the force, and we may obtain I B delta x delta y. Delta x delta y is certainly the area of the current loop, this area, the area of the current loop. So we obtain the formula IBS. And you remember that by definition, the quantity Is is called the magnetic moment of the current loop. And so the torque acting on the current loop will be the magnetic moment times the magnetic induction, the induction of the external magnetic field. Actually, the torque will depend on the angle between the magnetic field and the plane of the current loop. And I started from demonstrating that if the magnetic field is perpendicular to the loop, then no torque is acting on on this current loop. It means that the torque is 0. If the magnetic field is perpendicular, then the torque is 0. If the magnetic field lies in the plane of the loop, then the torque is maximum. So this is actually maximum magnitude of the torque acting on the magnetic loop. And if we want to calculate the magnetic torque from the external magnetic field at an arbitrary angle between the magnetic induction and the plane of the loop, then we will have to take into account this sine phi, the phi angle between the plane of the loop and the magnetic vector. But this is the maximum magnetic torque acting on a current loop. Another fact which we discussed important fact was the Lorentz force. The Lorentz force the force acting on any charge that is moving, that moves. And we underlined that if some force acts on a straight current placed in the external magnetic field, then some similar force must act on each element of this current, and no matter how small the element is, even if it's just a single charged particle. So if a single charged particle, a charge q, flies with velocity v, then it will experience such a force in the magnetic field. And the direction of this force will be perpendicular to the vector b and to the vector of velocity. So that if velocity is directed here and magnetic field is directed here to the blackboard, then we can use the left-hand rule to determine the direction of the force. So if the magnetic field is this perpendicular to the blackboard and going to the blackboard, then it must enter your palm of your left hand, and the sum will show the direction of this force, of this Lorentz force acting on a charged particle having the charge q and moving with velocity v. So this is the magnitude of this force, and the direction of the force can be found using the left-hand rule. Another important fact that we discussed was the magnetic interaction of two currents. If you have two currents, I1 and I2, they magnetically interact, and likely directed currents, straight currents, will be attracted, and the force of attraction will be defined as, it will be proportional to the first current and proportional to the second current and inversely proportional to the distance between the currents and directly proportional to the length of the section of the current, which is chosen to measure the force acting on it. In order to measure the force acting on a straight wire, we have to choose some section of this wire and measure the force acting on this section. And certainly there will be again this constant mu0 and mu over 2 pi which indicates the magnetic constant, and mu is the magnetic permeability of the medium in which the two currents are immersed, and 2 pi emerging in this formula. We discussed all these facts during the last lecture, and now we will discuss something new, fact number 7. about the magnetic field. Fact number 7 is Faraday's law of electromagnetic induction. Michael Faraday and Faraday's law of electromagnetic induction. Michael Faraday carried out his experiments with magnetic fields almost during 10 years. It was a long series of different experiments. And in the year of 1831, he published an article summarizing his experimental research. And the most important thing in this article was a new effect which he discovered. A new effect is called electromagnetic induction. So the effect of electromagnetic induction should not be confused with the magnetic induction. Magnetic induction is just a vector. That is, the magnetic induction, a vector which describes the strength of magnetic field. That is the magnetic induction. And here we talk about the effect of electromagnetic induction. That is something different. It's not a vector. It's not a field. It's a physical effect, a physical phenomenon, which consists in the following. If we take a wire loop and attach a galvanometer here, attach a galvanometer, a galvanometer is a device which measures very small electric currents. So if we attach galvanometer here, then nothing happens. No current is in the loop because there is no source of electric voltage and no source of currents. Just a wire, conducting wire with galvanometer, and the readings of this device will be 0 because nothing is attached, nothing more is here. But if we take a bar magnet, with its south and north poles and move this bar magnet closer to this current loop, then while the bar magnet is moving, the galvanometer will show some current. There will be some current in the galvanometer, in this loop. If we stop the motion of this bar magnet, then no current will be shown again. And if we move the bar magnet in the opposite direction, then the galvanometer will show the oppositely directed electric current. So the general conclusion is this. If the magnetic field which goes through this wire loop is in any way changing, if the magnetic field is changing, then there is a current in this loop. That's the phenomenon of electromagnetic induction. Magnetic field is inducing electric current. That's the meaning behind this word. The magnetic field B, if it's changing, then the changes, the variation of magnetic field is inducing the electric current. That is the effect of electromagnetic induction. And Faraday studied this effect in many different ways. He was moving different magnets, and he was trying to repeat this experiment in a different fashion, that is, fixing the position of magnet and moving the loop, the loop or the wire loop. Again, if we fix the magnet and move the loop, then the magnetic field going through the loop will change and the current will be the same, no matter what is moving, whether the loop is moving or whether the magnetic bar magnet is moving. in any way the current will flow here on condition that the magnetic field in the plane of the loop is changing. So Michael Faraday came to the conclusion that the strength of the electric current is proportional to the rate of change of a certain physical quantity, which he called a magnetic flux. A magnetic flux is such a quantity which is defined as the magnetic induction times the area of this loop. Magnetic induction times the area of the loop. And if this magnetic flux, this is the flux, if the magnetic flux changes in any way with time, then the rate of change of this quantity, delta phi over delta t, will define the strength of the electric current here. And there are many possible ways to change the magnetic flux. We may increase the magnetic field, or we may decrease the magnetic field. Then the flux will change. The flux piercing the surface or the area of this plane, which is inside the wire loop. So we may change the magnetic field, or we may change the area of the loop. We may change the area. We may somehow deform the loop and change the area. Again, the flux will change, and again there will be a current. So there are many possible ways to change this quantity. Actually, this formula is correct only in case we have a uniform magnetic field which goes through this area, and the field is perpendicular to the area. If the field is not perpendicular and if it's not uniform, then the formula will be more complicated. For example, if the field is not perpendicular to the surface, then we will have to take a so-called scalar product. What is the vector of magnetic field induction? You know very well. The vector of magnetic field induction shows the direction and magnitude of magnetic field in a given point. And what is the vector of the area? The vector of the area is directed perpendicularly to the area. That is in simple words. And if the magnetic field is different in different parts of this area, then we have to divide the total area into small parts, and we have to calculate such a product, scalar product of two vectors for each part, and then arrange a sum, and then sum up all these quantities for all the fluxes for every small area which is here, which is arranged inside this loop. So in general case, the formula is somewhat more complicated. You will study it later when you study a course of electromagnetism here at this institute. But at the simplest possible level, the formula is this one, and you may only know that this formula is correct when the magnetic field is perpendicular to the plane of the loop, and if the magnetic field is well, anyway, it's the S is the area through which the magnetic field goes. If you turn this loop by some angle, and the magnetic field goes perpendicularly to the blackboard, then the magnetic field will see the loop something like this if it's turned at some angle, and then the area will be what the magnetic field can see from looking from the side of this loop. So anyway, the change of this quantity calculated in this way, in this fashion will give you the magnitude of the current which flows here. So the current is generated, the electric current is generated by changing magnetic field, by varying magnetic field. Another important thing which we will consider is the direction of this current. So this formula gives you just the magnitude of the current, and the direction of the current is defined by a so-called Lenz's rule. Lenz's rule. The Lenz's rule was established by this physicist Lenz, who studied this effect and formulated the strict rule which can help you define the direction of the current in every situation, whatever happens here. So, and there are many different possibilities to change the flux. I told you, you may change the direction of the loop, you may change the area, you may change the magnetic field. It may be increasing, it may be decreasing. You may change anything here, and in any way the flux will change, and in any way that will cause the electric current in the loop. So Lenz discovered that whatever change takes place in the magnetic flux, the simple rule, whatever is the change in magnetic flux, the electric current will have such a direction as to mitigate this change, as to oppose the external change of magnetic flux. So, for example, we have a current loop, and the external magnetic field, which is perpendicular to this loop. And suppose the magnetic field is increasing. It means that we take the magnet bar, and we move this magnetic bar towards the current loop. The magnetic field is increasing. Then the direction of the current will be such that this current will create its own magnetic field, which is opposed to the increase of the external magnetic field. So the magnetic field of this loop, of this circular current, should be directed against the increase of the external magnetic field in order to diminish this effect, in order to oppose the increase of the external magnetic field. If you move the magnet bar in the opposite direction, if you move it here with the velocity minus v, then the external magnetic field induction will decrease in the area of this loop. It will decrease, and the electric current will have opposite direction. It will have opposite direction, so that the magnetic field of this loop will have the same direction as the external magnetic field in order to increase the magnetic field. So if you want to decrease the external magnetic field, the current in the loop will flow in such a direction as to oppose your intention to decrease the magnetic field. So whatever change in external magnetic field, the current will flow in such a way as to oppose this change in external magnetic field. This is the Lenz's rule, and this Lenz's rule is often denoted in this formula by minus sign, which is just reminding you that the current flows in somewhat opposite direction to oppose the change in the magnetic flux. So these are the 8 facts about the magnetic field These are the 8 facts which we have discussed and which you have to know and which you must be able to explain at the exam. And we will solve some problems. We will solve some problems related to these facts. For example, I have chosen this problem from Landsberg, problem number 15.4.3 from Landsberg. So it says that we have a coil which has a length x 25 centimeters, and it has a diameter. The diameter of the coil is 10 centimeters, and the number of turns here, the number of turns is 1000. And there is an electric current which increases by 1 ampere per second. 1 ampere per second. So the electric current flowing through this coil is increasing by 1 ampere per second, increasing by 1 ampere per second. So the question is, what electromotive force will be generated on this coil? We need to find the electromotive force. Say, let's denote it as E. What electromotive force is generated on this coil? Before solving this problem, I would like to make some additional theoretical explanations related to what we have discussed about the magnetic field. So, as far as the phenomenon of electromagnetic induction is concerned, if we have a coil, if we have a loop of current, and we arrange a change of flux, of magnetic flux here, there will be some current. But actually, in order to multiply this effect, in order to make this effect better visible and stronger, people take not a single loop of current, but many loops, which is a solenoid, And if we increase the magnetic flux through this solenoid, then the effect will be larger, and the current which flows here will be larger. And if we attach a galvanometer to the terminals of this coil, then the current will be larger. And if the current flows here, it means that there is some electromotive force. Some force is acting on the electric currents, electric charges, electrically charged particles, whether positively charged or negatively charged. Some force will act on the charged particles, and the positively charged particles will flow in one direction, while negatively charged particles will go in opposite direction. So if there is some force, it is called an electromotive force. An electromotive force. And also if there is some force which causes this current to flow, there is some potential difference which makes the current flow, and this potential difference is the electromotive force of due to this effect of electromagnetic induction. So by changing the magnetic flux through this coil, we may arrange for the current flowing, and it means that there is some electromotive force which is just the potential difference emerging here at the terminals of this coil. So if there is n turns in this coil, then the electromotive force will be n times larger than the electromotive force originating from a single coil. So this is the flux through the single coil, through the single turn, the single loop, current loop. And this is a Faraday law for electromagnetic induction in a single loop of the current, in a single turn of the wire. But if there are n turns in this wire, then the effect will be n times larger. Also, we can imagine such a situation that we have a resistance R and a solenoid here, and if there is a changing electromagnetic field which pierces this solenoid, it will cause the changing magnetic flux through the solenoid, and that will arrange for some electromagnetic induction and electromotive force, and the current will be here, and then the electromotive force E, which is measured in volts, will define the current according to the Ohm's law, and the current here times the resistance of the circuit, total resistance in this circuit, will be equal to this electromotive force. The electromotive force is defined by the Faraday's law of electromagnetic induction, and this formula will allow you to calculate the current flowing in this circuit if you know the electromotive force defined by the rate of change of the external magnetic field flux. And if you know this in volts, and if you know the resistance of the circuit, then you may calculate the current in this circuit. Well, all this is necessary, all these simple things related to the Ohm's law, which is nothing but the Ohm's law. All this is necessary to be able to solve this problem which we are discussing now. So another thing is that if you change the external magnetic field, then the current will flow and there will be some electromotive force on the terminals of the solenoid. But the reverse phenomenon is also observable. If you change the strength of the current in this circuit by any means, if you change the strength of the current, then the current will create a magnetic field in this solenoid, and the magnetic field will change its strength, its induction. If the current is changing, the magnetic field will change. Look here at the formula defining the magnetic field inside the solenoid with some current. If the current changes, then the magnetic field in the solenoid should also change, because it's directly proportional to the current. So if the current changes, then the magnetic field should change. But if the magnetic field should change, then the magnetic flux piercing the solenoid will also change. and that will cause the emergence, the occurrence of some electromotive force here. So if we change the current flowing through the solenoid, some potential difference is sure to appear here because of the Faraday's law of electromagnetic induction. And the logic is simple. The current flowing here creates the magnetic field. If the current is changing in time, if it's varying in time, then the magnetic field will be varying. And if the magnetic field is varying, then it will inevitably cause the electromagnetic induction, the electromotive force on the terminals of this solenoid. By the way, the direction of this electromotive force, of this potential difference, which appears due to the change in current, the direction of this potential difference, according to the Lenz's rule, will be such as to oppose the direction of the change in the current. If current is decreasing, the magnetic field will appear here such as to increase the current due to the law of electromagnetic induction. And vice versa, if the current is decreasing, the potential difference emerging here will tend to oppose the increase, that it will tend to decrease the current, according to the Lenz's law. So after all these comments, we may solve this problem easily. So we must calculate the electromotive force. We must calculate the electromotive force in this coil if the current flowing through the coil changing. It's increasing by 1 ampere per second. So if the current is changing, then we have to use this formula. The electromotive force will be proportional to the number of turns of the wire, and it will be proportional to the rate of change of magnetic induction. Magnetic field is created by the same current, and the magnetic field is changing because current is increasing with the rate of 1 ampere per second. If the current is becoming larger and larger, then the magnetic field here is increasing, and therefore the magnetic flux is increasing with time, and there is non-zero value of this expression. Delta phi is non-zero, and so magnetic field flux is increasing with time, and we have to calculate the action of this magnetic field on the current, which is increasing in this particular case. So that will be the number of turns, and delta phi is what we have to use the formula for the magnetic field created by the current. And the formula for the magnetic field created by the current is this one. The magnetic field will be so that will be the magnetic field flux, first of all, is the magnetic field B times the area of cross-section of this coil. The area of cross-section can easily be calculated because we know the diameter of the coil. So Bs is the magnetic field flux, and we have to calculate the change of this quantity, delta Bs, the change in time, and that will be the number of turns. Area is constant, it doesn't change, so the area of cross-section of this coil doesn't change, and we have only delta B over delta T. So Ns remains unchanged. And what is B? B is the magnetic induction inside the coil, which is defined by this formula. So we must calculate delta B is the magnetic induction, it's mu0, and the coil is empty, there is no core in this solenoid, so it's there is no magnetic permeability, which is just unity for the air. Magnetic permeability mu is unity. So we have to take into account that magnetic field B is determined by mu 0, the strength of electric current, the length of solenoid, in this case it's x, and the length of solenoid divided by the number of turns, because we need to substitute here the number of turns of the solenoid per unit length. So the total length divided by the number of turns, that will be the total length divided by the number of turns. That will be the number. I'm sorry. Sorry, this is something. This is wrong. I'm sorry. This is the number of turns per unit length. So I put it wrong. I should have written N over L, the number of turns per unit length. That's why I'm stumbling at this point. I see something's wrong. The number of turns per unit length, and unit length, and the total length is x. Total length is x here. So we are just using this formula for the magnetic field inside the solenoid, which is mu 0, and magnetic permeability mu is unity, and then the strength of the electric current and the number of turns in the solenoid divided by the total length of the solenoid, and this by time. And Ns remains unchanged. Mu 0 is constant. It doesn't change. The number of turns is constant. The length of solenoid is constant. And what is changing? Only the current. And the rate of change of current, delta I over delta T, is given in this problem. It's 1 ampere per second. So what we obtain here is simple formula. This is 1 ampere per second. And N divided by X is what? 1,000 turns divided by 25 centimeters. 1,000 divided by 25. Centimeters are not, centimeter is not a unit of an international system. So we must take it as 0.25 meters. So divided by 0.25. And mu 0 is 4 pi times 10 to the minus 7th power. And S can be determined as I want to calculate the cross-section area of the solenoid S. Cross-section area is related to diameter as pi diameter squared over 4. That will be pi diameter is 10 centimeters, which is 0.1 meter squared divided by 4. Well, pi over 4 is approximately 1. We will carry out approximate calculations here. Is approximately 1. So we have 10 to the minus second power 1/100th of a square meter. That will be a cross section, 10 to the minus second power, and N is 1,000. So substituting all these quantities in this formula will give us something like, let's do it correctly. 1,000 is the number of turns. Area of cross section is 10 to the minus 2. I will put it in this way. And then 4 pi is approximately 10. I will put it this way. And then 10 to the minus 7. Minus 7 will go here. And then 1,000 will be here. And then 1 ampere per second divided by 1 by 0.25, that is 4. That is the coefficient 4. And what do we have as a result? 4 times 10 to what power? We have to calculate the power of 10. 3 minus 2 plus 1 is 2 plus 3 is 5 minus 7 is minus 2. 5 minus 7 is minus 2. So it looks like something like 40 millivolts. If we take 1000, this is 1 millivolt, and this is about 40 millivolts, something like that. So we have found the electromotive force which will occur here at the terminals of the solenoid in case the current flowing through the solenoid is changing with the rate of 1 ampere per second. The current is changing, and then on the terminals of this solenoid some voltage will appear, and the voltage will be about a few millivolts. So what's the main thing in this problem? The main thing is to understand that if a current flows through a solenoid, through a coil made of several turns of the wire, then this current creates a magnetic field inside the solenoid. And this magnetic field, as it pierces the solenoid, it will create a magnetic flux. So if the current is changing, then the magnetic flux is also changing. And the changing magnetic flux, according to the Faraday's law of electromagnetic induction, the changing magnetic flux creates some potential difference. And if the current is increasing, as it's given in this problem, the current is increases with the rate of change of 1 ampere per second, then the magnetic flux change here will create such a potential difference which will be directed against the increase of the current according to the Lenz's rule. So this change of magnetic flux will create the potential difference which will cause the current flow in different direction. It will be opposed to the change in current. The current is increased by some external source, but the magnetic field which is here created will change in such a way it will increase, and it will create such a potential difference which will cause the current to flow in different directions so as to oppose the increase in the current. And how to calculate this potential difference which appears due to the change in current, not due to the current itself, but only due to the change in current in time. So how to calculate this potential difference here? That is how to calculate the electromotive force. We have just shown in this solution. It's a purely technical thing to substitute numeric values and to carry out calculations according to given formulas. This is purely technical thing. But what is important is to understand the physics of phenomena. What is happening here? What's going on? What processes and what phenomena are observed? What actually takes place here in this problem? Another thing I would like to discuss is the relationship between the Faraday's law of electromagnetic induction and Lorentz force. So there is a relationship between the Lorentz force and the law of Faraday of electromagnetic induction. And I will discuss this relationship right away. And I will need probably this part of the blackboard. So in electromagnetic induction, we have a changing magnetic flux. In order to change magnetic flux in a certain condition, let us suppose that we have a straight rod AB that can slide along the two straight wires, remaining always in touch with these wires. So there is, here we have an electric contact, but AB is not firmly attached to this, is not fixed on these wires, but it may freely slide along the wires, either upward or downward. And suppose there is a magnetic field here. The magnetic field goes perpendicularly to the blackboard, and it's directed in this way. So we have magnetic field induction, uniform magnetic field. We have a uniform magnetic field. And suppose this bar moves downward with some velocity, sliding along the vertical conducting rails, you may say so. You may say rails or wires. And there is a some device like galvanometer to measure the electric current which may originate here. And so actually if the rod moves in this direction, then magnetic field acting here will cause every positive charge to move in this direction and every negative charge to move in opposite direction due to the Lorentz force. Lorentz force acting on a charge that is moving in the magnetic field. Every free charged particle, every electron will be acted on because it moves downward in the magnetic field, and positively charged particle will be acted in this direction, and negatively charged particles will experience force from the magnetic field acting in opposite direction. But the direction of the current is determined by the motion of a positively charged particle, regardless of whether there are negatively charged or not, or regardless of whether there are positively charged or not. But the direction of motion of positively charged particle will show you the direction of the current, and negatively charged particles will go in opposite direction. So what happens here in this particular case? Let us suppose that the length of this road between points A and B, the length is known. Let it be the length, this direction, the length of this section will be delta x. And there is a force acting on each charged particle, which we know, which is proportional to the charge and proportional to the velocity and proportional to the induction of magnetic field. And the velocity is always some displacement delta y divided by time delta t during which this displacement occurred. So the bar AB was in this initial position, and then it moved downward with velocity v. And so this force acting on each charge will be given by q delta y delta t times b. If we take all the charges in this rod, all the charges q, and the time delta t during which all these charges go away from this rod, then this q divided by delta t will be equal to the current. So the current in this rod is defined by the total charge here divided by delta t, because the total charge will go through this cross section of the wire in time delta t. So that will lead us to conclude that this is a total current B delta y. Also, we may remember that in electrostatics, the force acting on a charge, on a charged particle, in electrostatics is defined by the charge times electric field strength in electrostatics. And the Lorentz force is defined by this formula. Comparing these two formulas, we come to conclusion that from the point of view of this charge, it looks like the charge is in some effective electric field, which is defined by this formula, the velocity of the charge times magnetic field. And this is not a real electric field. We have attached no electric voltage here, no electric potential difference. But the charge feels this electric field, and I call it effective electric field. Effective electric field. And so, if there is an effective electric field acting on the charge, then there is some potential difference between these 2 points. The potential difference, U, will be equal, according to electrostatics laws, will be equal to this effective electric field times the distance, delta x. That will give us E B delta x. And V is delta y, displacement in vertical direction by delta t. So this will be, if we substitute for V this expression delta y over delta t, we will obtain B delta x times delta y divided by delta t. And delta x times delta y, this is what? Delta x is this length and delta y is this vertical length. So if we multiply this section by this section, we will obtain the area of this rectangular figure. The area is So this will give us B delta S times delta T. And delta B is constant, so this formula will give you change of magnetic flux. Change of magnetic flux. Magnetic flux is Bs with time. B times delta S is the change of magnetic flux with time, the rate of change of magnetic flux. So what we obtain here is that the potential difference between these 2 points created by the motion of this rod in the magnetic field, the potential difference created equals the rate of change of magnetic flux here, which is actually the Faraday's law, which is the Faraday's law in the formulation of Faraday. By the way, Michael Faraday never graduated from any universities, and so he was not very likely to write many formulas, and in his written articles he used very small number of formulas. He practically explained all his discoveries without mathematical formulas, and he explained all his discoveries but just with words. And with words he used different words in different situations, but his discoveries were really great. What he discovered, sometimes he explained his phenomenon like the current flowing here, sometimes like potential difference, sometimes like electromotive forces. So he used different words in different situations. But actually this discovery is great. He hardly used any formulas in his works, and the formulas were written by other scientists, especially by James Clerk Maxwell, who put Faraday's discoveries and discoveries of other scientists into a beautiful system of differential equations describing the magnetic field. So according to Faraday's law, actually we have the potential difference between on the terminals of this rod will be defined by the rate of change of the quantity, which is called Bs, which is the flux of potential field induction here. And so what we obtained here, we started from the formula for the force acting on a single charge, which is a Lorentz force. And from this formula, in a particular situation, we obtained the Faraday's law of electromagnetic induction. So there is a very close connection between different phenomena in electromagnetism. And it's very often the case when one formula, like for electromagnetic induction, can be derived from another formula, and vice versa. They are intimately connected. All this theory is beautifully interconnected. And there is a simple question in this respect. Simple question is this: we considered many phenomena related to electromagnetic fields. I tried to count the number of formulas and phenomena from 1 to 8. From 1 to 8. Probably there are much more. There are more formulas and more phenomena in electromagnetism, certainly more. But we considered 8 different processes and 8 different phenomena. And there is a natural question: can this magnetic phenomena be somehow understood from some theoretical point of view? Can all these magnetic phenomena be derived from some basic and simple principles? Is there a theory which allows one to obtain all these formulas from simple axioms or simple principles? The answer is yes. we considered all these phenomena just like a generalization of experimental results. I always referred to some experiments, the Ørsted experiment and the Ampere's experiment for Ampere interaction between currents, parallel currents, and Faraday's law also explained as a generalization of some experimental results. And that was the way the electromagnetism was developing historically. People started from experiments and described experimental results with formulas, and then they generalized these formulas into some theory. But there is a natural question: can all these magnetic phenomena be somehow obtained from simple principles, simple theoretical principles? The answer is yes. All the magnetic phenomena can be derived from two simple principles. First, electrostatics. You may take and adopt electrostatics. And second principle is Einstein's theory of special relativity. If you combine electrostatics with special relativity, you may derive all the magnetic phenomena. So the magnetic field is a relativistic effect of electrostatic field. If you consider electrostatic fields described by vector E and apply relativistic formulas, relativistic ideas of special relativity, then you will theoretically obtain all the magnetic phenomena which we discussed with magnetic fields. And finally, I will probably have some time to solve another problem, which is problem 538. I think we have 2 or 3 more minutes to discuss it. Formula 538, problem 538. It says 583, certainly 583, problem number 583 from Buchovtsev. It says, well, it's considering the same situation as we have considered here. A rod is falling down, sliding along the 2 conducting wires, but here, instead of the device to measure current, here we have some resistance R. And it says, the problem says, what will be the velocity with which the rod will fall in the magnetic field of the Earth? What will be the velocity? So we have obtained it that we have obtained this result that if this rod falls down, moves down with some velocity v, then there will be a potential difference generated between points A and B. And the potential difference will be given by this formula of electromagnetic induction. And because the electromagnetic flux going here changes, the flux going through this loop changes in time because this rod moves down. And so there will be an induced current flowing here, and the induced current will be given by the Ohm's law. It will be the potential difference. It will be the potential difference between points A and B divided by R divided by the resistance. And the potential difference is given by this formula which we have already discussed. And so we may put it in this way. We may put it in this way that the potential difference between points A and B will be given as the velocity times the magnetic field here times the distance delta x, the length of the current, the length of the rod, here, and that will be, according to the Ohm's law, current times resistance. And so so the current can be found from here as the VB delta x divided by R. And so if there is a current, then there must be a force. If there is a current in this direction, there must be a force applied to this conductor, and the force applied to the conductor is proportional to the current, proportional to the magnetic field inductance, and proportional to the length of the current, the length of this rod. And so here, if we substitute here this expression for the current, we substitute here, we obtain that that will be V divided by R, and then B squared delta X squared. And also we know that if the force of gravity, in this problem, the mass of this rod is given. So we know that the gravity force acting on the bar on this rod is given mg. The mg force is acting downward, and the motion of this bar will be with constant velocity if there is no acceleration, and no acceleration will be in case the force mg equals the magnetic force applied upward. That is equal to VR V over R, and this expression B squared delta X squared. So under this condition, we can, this is just the condition for static equilibrium. Static equilibrium means that there is no acceleration, but there may be a constant velocity. In this particular case, the velocity of motion of falling down of this rod is constant, and therefore acceleration is 0. And therefore, the force of gravity directed downward should be equal to the force of ampere force acting from the magnetic field on this current. So the equality of these two forces provides for, ensures the that the velocity is constant. And then we obtain that the velocity with which the rod will fall down will be equal to mg r divided by b squared delta x squared. That will be the answer to this problem. The bar will, this rod will fall down with constant velocity in the magnetic field of the Earth, because the magnetic field will be balanced. The magnetic field force directed upward will be balanced by the gravity force directed downward. And so this bar will slide down with constant velocity. On this point, we will finish this lecture as the time has elapsed. And so next week, we will have 2 remaining lectures, and that will be the last week of our studies. And next week, we will consider some laws of classical optics. On this point, goodbye until next week.